So first of all, it's a pleasure to introduce our speaker of this month, which is Jesús de Loera. And he's from the UC Davis. He is very well known in mathematics, applied mathematics. Actually, he's a fellow of the American Mathematical Society as well as a fellow of SIAM. I read that you are new also vice president of the American Mathematical Society, one of the 3 vice presidents. And you received your PhD from Cornell University under the supervision of Bernd Sturmfels. And so I'm looking forward to your talk, Jesús, and the title, which is entitled The Geometry of the Space of All Pivot Rules for the Simplex Method. Thanks.
Thank you very much. Can you hear me well, everybody? Hope everybody can hear me. So this is a joint work with several wonderful people. There's actually 2 papers that you can find on the archive. And I will mention the work of with Alex Black, Sean Kafer, and Laura Sanita very briefly as part of the explanation. But the main part of the lecture will be a joint work with Alex Black, Niklas Lugerharms, and Raman Sanyal. And it is a very nice story that I hope demonstrates this to this community that geometry and algebra can be very applied. And I think this is a very nice story. So let's get going. So the mathematical question that we want to understand is a problem in optimization, which is very classical. It's called the linear programming problem or linear optimization problem, which is very simple. You have a system of linear inequalities, and you want to maximize or minimize a linear function that, in some sense, for reasons of computer science, let's say reasons of computer science calculations of complexity, I often will assume that these numbers are rational numbers. And as you know, the set of possible solutions of this system of equations or system of inequalities will be a convex polyhedron. In this talk, I will assume that it's a polytope that is bounded. Okay, so it's not going to make a difference for everything I say. And the problem, so the thing that we want to talk about in this talk is the simplex method. So the simplex method is one of the most influential algorithms in history. It's not me saying that. It is the SIAM said in the year 2000, they selected some of the most influential algorithms in the 20th century. And this is one of the top 10 algorithms by different reasons. And because linear programming and the simplex method are very, very important. Without the simplex method and linear programming, we will not have, for example, integer optimization. We wouldn't be able to count lattice points. We really will need the simplex method is also very fundamental because it has duality. So the duality theory is very well developed, and anyway, so it has a combinatorial flavor that you will see in a moment. So this gentleman is George Danzig, who invented the simplex method in 1947. And normally I teach students the simplex method in about 5 weeks. So I'm going to give you a discount, and I'm going to teach to you the simplex method in just 2 minutes. Okay, so here's a 2-minute presentation of the simplex method. So the simplex method, first of all, we know that if there is an optimal solution, there is an optimal solution that is among one of the 0-dimensional faces, namely one of the vertices of the polytope. Okay, and so you start at a vertex. So you pick, for example, this vertex that you see here. And if you have an edge, a one-dimensional face that improves, then you take that edge. So you go to the next point, and you go to the next point. Every time you have an edge that you can improve, you choose one of the edges that you can improve, and then you move down in the direction of the objective function. So in this case, the objective function is just going vertically, in some sense. Okay, but now, here is a very important point. I'm hiding the details here, of course, but there has to be a method to choose the best edge, because as you can see here, there might be choices, right? So you can see that this maybe here you have two choices of which of the edges, both of them have improvement. So which one should I choose, right? So this is essentially, you have by the objective function, you have oriented the graph of the polytope. So there's a directed graph that gives you, it's a complete orientation of the graph of the polytope, and you are just trying to find a monotone path in this polytope until you continue to improve and improve and improve and improve. And then finally, you get to a point where you cannot improve. And that must be an optimal solution. Okay, so that's in a nutshell. Of course, I'm skipping lots of details. Of course, for example, to make this in practice, you need to do some very effective linear algebra. And that took a lot of years, actually, to develop efficient, sparse linear algebra to do the updates. Because essentially, in all this pivoting, so when you go from one vertex to the other, we call that pivoting. So the pivots are essentially switches of matrices. So you're switching from one matrix to another that represents the vertex. So these are the planes. So every vertex is represented by a collection of planes that define the vertex. Now, I'm hiding all kinds of details, but one of the important details I have to stress now is the pivot rule. So the pivot rule is this way to choose the next edge, right? So you have choices on the edges. Which one should I choose? And the pivot rules are, yeah, so here it is. So the pivot rules, I'm going to define in some sense in a somewhat informal way. I'm just going to take a very broad sense of what is a pivot rule. It's a method, or you can think of it as an oracle for selecting an improving edge from a current vertex. I will explain later why it's not a good idea to try to define this as some kind of language, or, let's not get into the details. Is this a Turing machine or anything like that? Because you will see why in a moment. But I think it's important that you understand this. This is some kind of mechanism that we have available to you. By the way, when we teach this linear programming, we normally look in terms of the matrices that we are updating every time, and there's some criteria in terms of the matrices. So Danzig, for example, he used very much the matrix analysis or matrix calculations to do these decisions. Okay, now the very big question that has been open for a long time and is very important in the theory of computer science is there a pivot rule for the simplex method? Can anybody find a rule that makes this algorithm into a polynomial time algorithm? The answer is we don't know yet. And so far, the news look pretty bad. Ever since 1972, the first example was done by Klee, my academic grandfather, and George Minty here. Klee and Minty, they constructed these very fancy linear programs that are the so-called Klee-Minty cubes. So they are geometrically, they are cubes, or rather combinatorially, they are cubes. They are deformed cubes. You can see that one here. There's one here in red, kind of thing. It has some very tilted planes. It's kind of twisted cube, but it's combinatorially a cube. And so what Klee and Minty demonstrated is that if you take this linear program with this specific linear inequalities, and then you take an objective function that is just very simple and apply one of the pivot rules, the so-called Danzig pivot rule, you take a walk, the monotone path is actually all the vertices of the cube. So it's an exponentially long path, exponentially in the dimension, okay? Now, you might be saying, oh, come on, Jesus, I look at the book and I know that the Klee-Minty cube has horrible numbers. It's not going to happen to me, da, da, da. Well, I mean, in 1973, Norman Sade, he showed that even in the network simplex algorithm, so the network simplex algorithm is essentially the simplex method applied to network flow problems. And there the numbers are very nice. I mean, the matrix is just 1, zeros and minus ones, right? It's the mean cost flow problem. So there's no nasty numbers or anything like that. So it is very nice, but there's also an exponential number of vertices that you can visit in that case. By the way, are you with me? I mean, I don't know whether I can see you asking questions or anything like that. So if you have a question, just stop me, okay? Or I don't know, unmute yourself or shout or something, okay? Okay. Okay, so there are millions of pivot rules, and the pivot rules, there's essentially one pivot rule for every person in the planet, okay? You have your own pivot rule with your name someplace in the planet. So I'm not going to go over all of them. I'm just going to highlight a few of them that are very interesting. But again, I'm just scratching the surface here, okay? So one of the, okay. Yeah, one of the most famous ones is, of course, Danzig. And again, this is given in terms of the matrices. So I'm not going to go over that one, but it's the first one historically. The ones that I would like to discuss are the more geometric ones that we know more about. By the way, yes, I mean, I'm giving a very geometric presentation of the Simplex method because it's a geometry seminar, right? I mean, or algebra geometry seminar. So you will see a lot of the emphasis on the geometry. I mean, there are other very important pivot rules, like the Blanche pivot rule is very important because the one issue that the Simplex method has is cycling. So you may stay on a vertex many iterations, because remember, when you are at a vertex, there might be many planes that represent the same vertex. So for example, if you have like a icosahedron, you know, I can choose any three of these planes and they intersect on the vertex. So that will be one of the iterations, but I can switch to choose any other triple of planes. So it can happen that you stay there forever, just going around the same vertex, but different representations of the same vertex. And the degenerate polytopes happen everywhere. So anyway, so Blanche's pivot rule uses a lexicographic ordering on the planes that involve this polytope to choose who's the next pivot. And one can use this actually to avoid cycling. So that was kind of an interesting achievement. And for those of you that don't know this, Blanche's pivot rule is also applicable to oriented matroids. So this is very highly connected to the theory of matroids. For those of you that love matroids, I know some people in the audience like matroids, eat the matroids for breakfast. So anyway, so the ones that I want to highlight today are a little bit different because they are more geometric, and you will see they are very important. So the one is greatest improvement rule. This is kind of very greedy way to go about it. You have several edges to choose from, and you choose the one that maximizes the overall gain. So there are many options. You know, you can go all these edges, and you just choose the one that gives you the most gain. Okay. Now, the next one is called the steepest edge rule, and that's very similar. So you choose an edge that maximizes the gain, but you need to divide by the length take into account the length of the edge that you are moving on. So that's why you divide by the norm, by some norm. In this, most typically people divide by the L2 norm, and the steepest edge rule is actually the most popular pivot rule in practice. So that's what, if you buy software, that's essentially what people use in practice, the steepest edge. Here's another one that is kind of fun. Random edge pivot rule. Choose a random edge. Just any of the improving edges you have, just choose one at random. That's the random pivot edge. And random pivot rules are actually very important in the theory of linear programming, because they were more or less, they had a very good performance analysis, and there was a lot of analysis of the pivot random edge. Sade's rule is actually kind of interesting because it takes history into account. And this is something we're going to see is important. You choose the least enter plane so far. So you choose the least enter non-basic variable. So that would mean that you're choosing the edges. Okay, so that's, let me now take one moment to highlight an even more, I would say, perhaps the most successful pivot rule in theory, in the theory of computers, in the theory of algorithms. So this pivot rule is called the shadow vertex pivot rule, and the idea for a geometry is very natural. So you have this linear program, right? This is your linear program. Remember, for a geometer, a linear program is just a polytope with an oriented graph. That's what a linear program is, right? And you have an objective function. This is your objective function. So what I'm gonna do is I'm at some vertex. So I choose another objective function, which I'm denoted here by psi. And I will use these two objective functions to do a two-dimensional projection of the polytope. So if I choose these objective functions, you know what you see, the projection will be this plane. This is the plane of projection. So you get the shadow is the projection of this polytope by these two linear functions. Okay, so you get a two-dimensional object. You get a polygon. I mein, of course, polygons are trivial, right? Because you have an up and a down. So you have two paths. It's easy to choose which one to go. So you essentially you do this two-dimensional projection, and that gives you a way to walk from the initial point to the optimal. Okay, and the thing you want to do is that, of course, you need to break ties on top. So you want to do the walk on top, not on the shadow, but you are doing the walk on top. And that walk essentially is going to be okay because the way you choose psi is normally a very non-degenerate way. So there will be a unique path here on top that corresponds to the shadow. Okay. Now, these paths that I trace are called coherent. I call them coherent because in honor of the constructions of regular triangulations and fiber polytopes. You will see in a moment. But I mean, you might say, well, that's beautiful, but is this going to be an efficient pivot rule? And unfortunately, without any extra work, this is not going to be very efficient because there are exponentially long shadows, even for very nice polytopes. Okay. Any questions so far? Okay. Yes. So one of the reasons I wanted to highlight the shadow vertex pivot rule is because, as I said, essentially you generate a bunch of paths depending on the different two-dimensional shadow projection that you do, the choice of the psi that you make, right? And what you get is, surprisingly, is a polytope. It's a polytope whose vertices are in bijection with all the coherent monotone paths, all of them. Okay, so this is essentially a beautiful object that was first. I should put it here. So this is essentially part of the theory of fiber polytopes that was started in 1990 by Loera and Sturmfels, right? Loera, Sturmfels, and it has had a lot of interesting connections. For example, secondary polytopes that count triangulations, regular triangulations, are special cases. And this is another special case. This is the so-called monotone path polytope. Monotone path polytope. And the beautiful thing is that I'm showing you this because this is an example of the kind of theorem we're going to prove to you today. I mean, I'm going to show you today. I don't know whether I will prove it, but I will show it to you, which is that there's a polytope that classifies all the objects that you want. And in this case, this polytope is classifying all the monotone paths, all the shadow vertex paths. Questions? So yeah, by the way, so in the case of the cube, so that's why you see a cube and a permutahedron here, is because the monotone path of the three-dimensional cube is a hexagon. You know, it's this hexagon that you see here. And you can see all the monotone paths, all the coherent monotone paths are in green in the cube here. You can see the green monotone paths, right? And so this is in this case is a hexagon. If you do it for the four-dimensional cube, you're gonna get a permutahedron. So in general, it's a permutahedron. The monotone path polytope of the 0, 1 cube. Okay, so now you might be saying, Jesus, you are so pessimistic, man. I mean, you are just telling me bad news. Well, I will try to give you some good news, okay, for a change. So some positive results, but most of the positive results so far on pivot rules are actually about stochastic pivot rules. So in 1982, Heinz Borbart, so he decided to analyze the simplex method when you sample the constraints from a specific distribution. So you're sampling the constraints from very specific distribution of polytopes. So the polytopes come from a specific probability distribution. So then you can prove for a fixed distribution, there were theorems that tell you there's an expected polynomial time, expected number of iterations for the simplex method for these random instances. And there was a similar analysis done by Adler, Megiddo, and Todd, by Stephen Smale himself, where you look at different models of random polytopes and you try to predict what's the random behavior, what's the expected behavior there. But again, here is not all polytopes, right? You have specific polytopes that are randomly generated from some specific distribution. There was analysis I mentioned already of random pivot rules, where essentially the people were excited because you got exponential number of pivots. So it's not quite exponential; it's a little bit milder than exponential, and this was for a while the excitement that maybe the random pivot rules are going to be the winners of the game and everything. But then later, in about 10 years ago, there was, about 10 years ago, there was examples that they are actually bad. They're exponentially bad. So they can reach these upper bounds. They can be reached. So no. But there was other development, the so-called smooth analysis of algorithms. So the smooth analysis of algorithms is an exciting topic in computer science. So where instead of worst case analysis, where you look at the worst case as a prediction of what can happen with an algorithm, or you look at average over a specific random distribution, you do the following. You take an instance that is probably very bad, and then you perturb it, for example, with a Gaussian noise. So if you do that for the simplex method, so you perturb the original polyhedron randomly with some Gaussian parameter sigma, then the expected number of iterations is going to be polynomial in the input size and 1 over the noise that you use. So that was observed by Spielman and Teng and many other people. And most recently, there's a lot of work by Dadouche and Huberts on this, on making this. But the interesting part is that they use the shadow vertex pivot rule, actually. So their analysis relies on the shadow vertex pivot rule. So shadow vertex pivot rule has also been interesting to analyze. Again, you're analyzing some kind of expected number of steps. It's probabilistic analysis that even for another parameter, even if you don't have noise, you can analyze by a measure of how flat the polytope is. You can think of this as the largest subdeterminant, how thin the cones at the vertices are. For example, totally unimodular matrices are very thin in this sense. The determinants are plus minus 1, so there's a good performance of the algorithm. Okay, so let me just stop here for any questions that you may have. Okay, so now let me tell you some. Yes, so Cynthia. To get a monotone path polytope, the input is a polytope, a linear objective function, and a starting vertex. No, to get all you need actually is the polytope, the linear function, and we assume that the starting vertex is always the mean of the objective function. I mean, you have an objective function as well. Yes, yeah. The way I presented it sounds that I'm starting at any starting point, and you can reduce that to what I said by adding an extra point far away. Yeah. Okay. But yeah, when Vilera and Sturmfeld presented these kinds of things, they computed from a polytope and from the LP, essentially from the LP. Okay. Yeah, but again, it's a beautiful object, right? It parameterizes all possible monotone paths that you can have. And okay, so here are some positive news that are deterministic. So you would like to come up with deterministic analysis. I mean, if you're like me, I mean, I love randomization like everybody, but you know, I have a soft spot in my heart for deterministic theorems. And I would like to show you that, you know, deterministic analysis is possible. So I think one of the most famous results is from 1997. Jim Orlin showed that the network simplex algorithm, he came up with a pivot rule, which is, I'm not gonna tell you where it is. Sorry, you know, it's a little bit complicated, so I'm not gonna tell you where it is. But you can actually run the simplex method for network simplex. So in the case of network flows, you can run it in polynomial time. Yeah, there's a specific deterministic pivot rule to do that. Okay, and there's lots of questions whether other pivot rules, simpler pivot rules, can actually work in this case. Okay, but now more recently in 2021, we try to look at what happens with pivot rules on 0-1 polytopes. Now, 0-1 polytopes are very important. You know, just think about the traveling salesman polytope, the matching polytope, the Birkhoff polytope. You know, pretty much in combinatorics, if you like combinatorics, and I know a lot of people here like combinatorics a lot. So if, you know, they're going to be 0-1 polytopes, you know, matroid polytopes. Now already you are salivating, right? Or matroid polytopes, very exciting. Okay, so all these are 0-1 polytopes, right? And yeah, so what happens with 0-1 polytopes? First of all, the first thing that happens with 0-1 polytopes is they're really degenerate. They're really degenerate. There's a lot of facets coming into a vertex, many more than the dimensions. So these are, you're gonna have to deal with degeneracy and cycling possibly, right? So everything I'm gonna say is gonna explain, nevertheless, something very interesting we found. So again, steepest edge pivot rule is very popular in practice. And we managed, so this is joint work again, you know, Alex, Sean, and Loera. It's a very fresh paper. You can still get it fresh from the archive. Yeah, if you pick the steepest edge pivot rule, we can actually prove that the number of non-degenerate steps, so that means the number of steps that you take to go, I mean, every time you improve, you know, every time you really change a vertex, right? You might spend millions of steps in one vertex because you are degenerate and you have to do some kind of bland pivot rule to get out of there, right? Somehow. But every time you improve, you're not going to need more than polynomial number of non-degenerate steps. Yeah. So that's good news. And yeah, so this is actually kind of nice. Then we also have something even better, actually, which is we have a variation of the shadow vertex pivot rule where you need no more than n. I forgot to say here. So you're 0-1, you have a 0-1 polytope, and I don't care how you give it to me. So I'm taking the most general possible representation of the 0-1 polytope. So it can be a system of linear inequalities together with some equations, right? But the number of variables is n, and the dimension is d. And normally d is less than n, right? That's typically the case. Like in the Birkhoff polytope, I give you n square variables, but you only need n minus 1 square of them, right? Okay, so yeah, so we found some variations of the slim shadow vertex pivot rule, and the order shadow pivot rule that actually show you that there's linear bounds, right? There's actually linear number of steps you need. And in this case, for the slim shadow vertex, you need no more than number of variables, many non-degenerate steps. And for the other one, you need no more than the dimension. Now, this last one is best possible because of the famous results of Nadev. Denis Nadev in the 1980s, he proved that the diameter of 0-1 polytopes, I should put his name here, Nadev. Maybe I have an extra D. I think so. It's double F or double D. I don't remember. So Nadev, he showed that the diameter of 0-1 polytopes is just D, is the dimension of the polytope. It doesn't have to be the ambient space, okay? And in fact, I mean, it's at most. Isn't that, for example, the Birkhoff polytope has diameter 2. Somebody has a question, or was somebody coughing just like, no? Okay, very good. Yeah, so let me just say a little bit about what the shadow pivot rule is, because it's going to be a very nice introduction to the other ones that you're going to see later. Yeah. So the pivot rule is actually going to kind of depend on the, you're going to do shadow vertex, but you're going to do shadow vertex, different projection at different vertex. I need to tell you what the vertex is. I really need to tell you what the vertex is. And the vertex that I'm going to take, it's going to depend on the vertex that you start with, and that will determine the second objective function, right? You have the objective function C transpose, and I need to tell you a second objective function B transpose that is going to give you my two-dimensional projection. And essentially, the objective function is this one here that you see here. See, if you start at the point at the vertex x0, which is a 0-1 point. Remember, it's a 0-1 vertex. So you get V0 is this thing here, V transpose. So then what you are geometrically doing is you are following the shadow path given by the projection as before. You're following the shadow path given by the two-dimensional projection given by these two objective functions. But remember, there's degeneracy. So you need to have some kind of criterion on top, right? I need to do the calculations on top, on the original Polytope. I'm inspired by the shadow, but I don't use the shadow in some sense. So, and this is the criterion. If I'm starting at the point xi, right? I'm like xi, and I have several of these edges going out from, xi. So I choose the edge, the neighbor u. So you're going to choose the neighbor u from xi. That is going to maximize this ratio, right? You have this ratio of it's a quotient between the value at C transpose and the value at B transpose, okay? So it's some kind of slope measure of how slopey, the slope on the two-dimensional projection of these things. Anyway, if you do that, let me just, I'm not gonna, this gives you linear number of steps, and I will show it to you with one example, essentially proof by example. So here's a proof by example. If you take this objective function C transpose, and I start at 0, 0, so then my objective function will be just counting how many non-zeros are there in each point. So as you can see, what I'm doing is I'm layering. I'm doing layers, right? So I'm doing the layers here of the 0-1 Polytope, right? And so that means that as I do these layers, every time I improve, I have to go to another layer. If I really improve, I have to go to another layer. And so that means that the number of improvements is not going to be more than the number of variables, right? So that's the kind of the idea here. But this is really a two-dimensional projection that you get, the two-dimensional projection of the 0-1 cube that you get from doing this and that as the projection in some sense. This is that point of view. And in this case, the monotone path that you trace will be this one. Are you with me so far? So some good news. So there are the nice pivot rules for specific families. But again, remember some kind of the motivation that I want in this talk, the main result in the last 20, how much time do I have? 25 minutes, 27 minutes, I think.
Yeah.
Okay. Yeah. In the last 27 minutes, I will talk to you about trying to classify all pivot rules. Okay. Yeah, so I'm going to explain some kind of taxonomy of pivot rules that, if we are lucky, is going to help us understand the complexity of all the pivot rules. So remember, we want to find some kind of organization of the pivot rules that will let you talk more about the complexity problems. So, and as a result, we're going to identify a very special family of pivot rules called which we baptize the memoryless pivot rules, and they emerge as the kind of the most important pivot rules to some extent, at least from this point of view. And the other thing that is very exciting is that we get a parametrization of all pivot rules, so it becomes a polytope. So as I will show you, this space has the structure of a polytope, and what is really cool is it generalizes the earlier constructions, like the fiber polytope construction that you saw from Loera and Sturmfeld. So that's another super cool thing. So you get some really nice things, and you go back to history and connect to the early history of polytope theory. All right. Any comments, complaints, or anything? No. Okay, let's get going. So I told you, you should not try. How should you think about the pivot rule, right? How should you think about the pivot rule? So locally, the pivot rule is making a decision for you. It's making a decision for you. So, but how should you think about pivot rules? You know, is it an algorithm? Is it some kind of language? Is it a Turing machine? What is it, right? And I claim that it's not a good idea that you try to do that, and we'll try to give you just evidence that this is a bad idea. So if you phrase pivot rules as decision problems, they can be very complex. For example, it was proved that they can encode NP-hard problems. So these wonderful people, Adler, Papadimitriou, Rubinstein, these Dicer, Scutella, Fernley, and Savani, all these guys have written papers where they show that you can phrase NP-hard problems as pivot rules or questions on the pivot rules. For example, you give me an LP, you give me a linear program, and you tell me a vertex, a particular vertex of your linear program. And then you say, hey, if I run my pivot rule, is it gonna pass through this vertex? Is the path gonna pass through this vertex? Well, that's an NP-hard problem. Okay. And this happens in many pivot rules. For sure, it happens in Danzig pivot rule. Surprisingly, shadow vertex does not have this property. Actually, shadow vertex, I guess, because it has to do with the shadow, and it has a lot more information, as you will see. It's actually polynomial time decidable to do this. This is something that Adler, Papadimitriou, and Rubinstein did, and yeah. So see, that's yet another reason, because you cannot expect to explain pivot rules as some kind of procedure if you cannot explain NP-complete problems, right? So you have to use a different approach. But we are geometers, right? We are geometers, so we're going to use geometry to classify pivot rules. So here comes the main definition of yeah. So the plan, here's the plan again. We're going to use geometry to classify pivot rules instead of using some kind of algorithmic classification that has to do with circuits or logic or anything like that. So we're going to use the geometry. So the definition of is the footprint of a pivot rule. So the footprint of a pivot rule, remember, you have already, when you have a linear program, you have a directed graph, right? You have a specific directed graph of the polytope, and the pivot rule starting at a vertex is going to follow some path, some monotone path from that vertex to the optimal. So I just take the union, the union of all these directed paths, subgraphs, right? I take the union of all these monotone paths, and that produces some subgraph of the original directed graph of the polytope. All right. So that's the footprint. And okay, so how complicated can be the footprint? Well, we'll see. Okay, and now let me get right away to the main definition of this talk, I guess, is that I'm going to say that a pivot rule is memoryless when I look at its footprint and I get an arborescence. So that's a directed spanning tree that it has a unique root, the unique root which is the optimum. All right. So it's the simplest graph I can possibly get. I just get a directed tree. Are you with me with this definition? I'll show you some examples and not examples now. Yeah, but yeah. So by the way, there are other equivalent ways to phrase what a memoryless pivot rule is. But essentially, you're standing at a vertex and you make a choice that only depends on the current vertex, right? You're at that vertex, you can just look at nothing that happened before matters in some sense. Okay, that's why we call it memoryless. Okay, what are some examples of memoryless pivot rules? Well, greatest improvement for sure, and steepest edge, because there, I mean, you're standing at a vertex, you look at what gives you the most improvement in some criterion and just take that, and there's a unique one, right? So that means that you're going to have a spanning tree. you're gonna get a 3 in this case. Okay. What are some examples of things that are not memoryless? Well, certainly you remember I mentioned SAGA pivot rule that uses the history. So you need to remember something about the previous variables you use. That's actually not going to be memoryless, of course. And shadow vertex is not memoryless because it's going to depend. So if you're a different vertex, you might actually do have the following phenomenon. So one of the paths might go here, you know, go to the optimum here, and then you start again in a different place, and you are going to cross and do this, something like this. It can happen that because you need a different projection depending on the vertex that you start, and that's the problem. Okay, so you may create cycles that make it not memoryless from the geometric definition that I gave you. Are you with me so far? Is the definition clear? Okay. Yeah, but so again, when you have memoryless, you have arborescences, and this is very important because we can do all kinds of things. For example, we can count them, right? We can count them, and I'm gonna say something that is to me is the most exciting part of this work. You know, Cynthia gives me a pivot rule, and her pivot rule might not be memoryless. You know, I don't care, because inside every memoryless pivot rule, there's a spanning sub-tree, right? There's at least one arborescence, and the arborescence is uniquely identified with the pivot rule in some sense. You can think of it. The advantage of memoryless pivot rules is that they give you an arborescence, and the arborescence gives you the pivot rule back, right? You can read it from the spanning tree. So in some sense, the memoryless pivot rules are the shortest pivot rules, the ones that really have the most essential edges in some sense, the most essential edges. So imagine that you can prove that every memoryless pivot rule has an exponential example. Well, then you pretty much are done with this question of possible polynomial time, because those will be really the shortest paths that you can have. Okay, now I want to, so far I told you, okay, here are all pivot rules, all pivot. Then I have here memoryless. And I want to, first of all, show you one more family that, so the memoryless and contain this, what I call what we call the NW normalized weight pivot rules, the NW pivot rules for short. And yeah, so this is going to be so reminiscent to the shadow vertex. You will see why, you know. So this is inspired in some sense by shadow vertex, or some of the definitions I gave you, I gave you before. So you need 3 ingredients. So you have already the objective function. So you have the objective function that I gave you with the linear program, and you need a weight. You need a weight that you should think of it as another weight, as another objective function. It's another objective function. And then I have a function that is a normalization, and you should think of this as a norm. So you see, that's why I'm hinting that the steepest edge and shadow vertex are inspirations for these things. So remember, you have your, I'm going to make a cartoon here. You are here at the point xi, and you have a bunch of edges that are sticking out, right? They're sticking out. These are the improving edges. There might be some idiots that come here that are the incoming edges, right? But anyway, you have the improving edges, and this orientation was given to you by C, right? This orientation was given to you by C. But I can think of the normalization as a way to shorten the edges or to normalize the edges. For example, I can imagine that I cut this with a, so the normalization here is maybe some kind of ball, right? I have a ball, and I have these are the new points that I'm considering. These are the new edges here. At the same time, this W is also allowing me to do some ordering of the edges by the W. So the formula that we have provided here is that the way you should choose a neighbor is by looking at the ratio between W and the norm, right? The W and the norm. And then you choose, of all the ones that are improving neighbors, you're going to choose the one that maximizes this ratio. And again, this coincides naturally with some of the definitions I gave you before. If you pick the right choice of W, the right choice of eta, right? This is motivated by that. So this tells you that a lot of the pivot rules that you love are actually going to be NW rules and NW pivot rules. Yes. So this is again, you have it's a 3-parameter family, right? This is important. It's a 3-parameter family, C, W, and eta, right? You have these 3 parameters. And yeah, here are some examples. Let me take some water. Yeah, so for example, the greatest improvement, the choices just make using what's that gives me the greatest improvement on C, and I don't care about the normalization, right? The normalization there was ignored. So that's just, you have eta is just the constant, it gives you just 1, and W actually equals to C. That's okay, you can take W equals to C. Similarly, steepest edge will be, again, you have W equals to C, and you have some norm, some LP norm. This has been studied. Again, I mentioned the 2 norm is the most popular one. In our theorem that I mentioned before, we use the 1 norm. So those are the 2 that I think have been, but there's at least one work by the Japanese school of optimization that they look at the general LP norms. There's another one that we call here, this is our invention, the max slope. And here we are using the objective function itself to normalize. And there you see, then you get really C transpose divided. So it's essentially the shadow vertex, right? This is the philosophy that I showed you before with the shadow vertex, where you're looking at the the slope of the projection. So you choose of all the edges that go out, you choose the one that has the maximal slope on the under the projection, on the 2-dimensional projection. Any questions about NW pivot rules? So I told you, you have the memoryless pivot rules, which are not all pivot rules, right? We know for sure memoryless is a special family of pivot rules. How about NW rules? Are these equal to all the memoryless pivot rules? I mean, because these are memoryless, actually. These are memoryless. All you need is the local information to know what's the next edge. You have a unique outgoing edge chosen, right? And the answer is no, not all memoryless pivot rules are NW rules. And let's see, yeah. So this is an example to show you. This is a memoryless pivot rule because I gave you a spanning tree, right? So here's a spanning forest, but arborescence. But if I memoryless, I need to be consistent, right? The one thing that memoryless pivot rules have is if you have the same edge directions, you should be consistent on your choices. And you see, this is not consistent on the choice. This is a non-consistent choice, and therefore it's not NW. NWs have to be very consistent. So what do I mean by that? Look at, let's see. Yes. So I think the trick is here. So you have 0, 0 and 0, 1, 0. So the edges there, you need to have the same choice. I mean, you have definitely this one, and this one, right? So you should actually you should have chosen here this one over this one, I think. Yeah. So the choice is not consistent because, so therefore it's not an NW rule. It's a memoryless pivot rule, but it's not NW. All right. Right. Okay. So, but there are good news. So here's it's really cool. In linear programming, in practice, we always perturb the data. We always perturb the data because we hate degeneracy, like in 0-1 polytopes. So we just perturb the data before we run the linear program anyway. And so we have a very nice lemma that says the following. So if you have a polytope in general, as I showed you in the previous example, in some sense, the edge directions matter, right? The edge directions matter. And if you have a polytope that all the edge directions are different, you have, essentially you don't repeat edge directions. You you have this phenomenon that then NW has to be really equal to memoryless. Okay, and so in general, this is true for a random perturbation of the LP, which is what we do in practice anyway. So in other words, a memoryless equals NW. Memoryless is a parametrized family. It's a parametric family, and it's only in 3 parameters for most perturbations, for most linear programs. Are you with me? So in some sense, the NW memory, the NW rules give you a way to look at all possible memoryless pivot rules in just 3 parameters. It's a 3, it just depends on these 3 parameters, C, W, and A, and the normalization. And then, again, the philosophy in linear programming is what happens when you change the objective function? What happens when you change the right-hand side? That's parametric linear programming. We study all these phenomena in linear programming. When we teach students sensitivity analysis, and especially in applications to finance, we teach them what happens when you change the one parameter. What happens, right? So we would like to understand this what happens with the linear with the pivot rule as you change W. How fast can you change the W and you still have the same pivot rule, right? The same arborescence. Or what happens when you change the objective function? So you guys know that when you change the objective function in a linear program, the same vertex is going to be selected as long as you pick the objective function in the same normal cone, right? The normal cone of a polytope. So you have your polytope, and this vertex is going to be the optimum as long as you pick the objective functions inside this cone, right? The normal cone of that vertex. So yeah, so that's kind of the plan. So I'm going to tell you what the theorem says. So you fix a linear program and a normalization. So you have fixed C, fixed normalization. And now I'm only going to change the W for a while. That's going to give me a different arborescence, right? Every time I have a different W, I get a different arborescence. And yeah, so, and again, in honor of the fiber constructions, we call this coherent. Yeah, so what is the collection of W that yield the same arborescence? That's going to be some kind of cone. And here's the main theorem. So we know that if you have two, essentially this comes from a polytope. So you're going to have a polytope that gives you the same arborescence. If you have two W's that give you the same arborescence, they correspond to the same vertex. And yeah, this polytope classifies all these choices of W, okay? And so it's a parametrization of all the arborescences possible. Any questions, comments? Okay. And again, this is very much in the spirit of parametric linear programming, where we had the same polyhedral fan classifying this. So now we can consider the case when W and C are the same. So as we did for steepest edge or for greatest improvement, and we let them change continuously, simultaneously, right? They are the same and they change simultaneously, but we fix the normalization. We still get another polytope. By the way, those are pivot rule polytopes or pivot polytopes. And so we get a similar kind of answer that all the pivot rules. So now you get, again, this is the formula that allows you to choose the next update. And what you get is what we call a neighbortope. A neighbortope because in this case, I don't know, you really look at just the neighbors of the vertex. It's a nice name. Okay, so now you have a similar classification in that for every two of these objective functions are going to give you the same arborescence if they correspond to the same face of the polytope. So the polytope parameterizes all possible, finitely many possibilities that you have of arborescences in some sense. All right, so a few examples. that will show you that this is not such a bad subject, and maybe some people like algebraic combinatorics very much in this audience. So I will hopefully they will like it a lot when I mentioned that, you know, if you use the constructions that I told you a moment ago, for example, you apply you compute the pivot rule polytope for the cube, and then you're going to see that that you have the permutahedron. You obtain the permutahedron. Pivot rule polytopes for the simplex are going to give you the associahedron. So you recover these classical important objects in algebraic combinatorics naturally from this construction. I mean, it's very nice because yeah, I don't know whether Raman, I think Raman was in the audience. He might know more about an algebraic combinatorics explanation, but this is nice to me that it comes from this optimization explanation in some sense. Yeah, so neighbortopes the same. So you get, in that case, if you take P, the linear program, or the polytope to be the hypersimplex, and there you have the permutahedron again. You can get a type B permutahedron if you take a P, the cube. So these are very classical objects, and I only have 2 minutes left. Let me see what I can say about this. Well, okay, let me try to make a relation to the. So remember, I mentioned the monotone path polytope, right? The monotone path polytope, and it turns out that the pivot rule polytopes and the monotone path polytopes are related by the notion of Minkowski sum. So when you have, let's see, let me go to the theorem directly here. Let's see, I think I can. Yeah, so I already mentioned the monotone path polytopes. They were the ones that classify the monotone paths, the coherent monotone paths. So it turns out the monotone path polytope is a Minkowski summand, a weak Minkowski summand of one of these max low pivot polytopes, okay? Pivot rule polytopes. And in the case of sonotopes, when you have your LP is a sonotope, you actually have the two things are actually exactly the same thing. So that's a really nice coincidence. Well, no, it's not. I guess not a coincidence. It's a beautiful connection to the constructions of fiber polytopes that we had before. Okay. Let's see what else I was going to say. I mean, there's connections to other types of polytopes that have been studied by Arnaud Pradrol and collaborators. Let me not, since I'm running out of time, let me just go to my conclusions. So finally, let me just summarize in the last minute I have. I hate people that go over time, so let me just try to finish on time. So there are many pivot rules, but we have shown you that there's a very nice structure, a polyhedral structure inside the space of all pivot rules. It's a parametrization of all pivot rules in some sense. The memoryless are the ones that are the most important because they are in some sense the thinnest by arborescences. And yeah, so we have these pivot rule polytopes. Again, already I mentioned if all memoryless pivot rules are exponential, then we are done with this question. So that's why it's interesting to understand memoryless pivot rules as well. I show you that memoryless pivot rules are essentially normalized normalized weight pivot rules for special perturbations of the polytope. So they can be parameterized. And I also show you that there are some very nice connections to geometric combinatorics, connecting to the monotone path polytopes and fiber polytopes in particular. And I thank you very much for your patience. The paper, oh no, the paper is on the archives. The papers are on the archive. I should have updated my slides. Thank you very much. Gracias, danke, in honor of Raman that is here and all the German speakers. Thank you.
Thanks a lot, Jesus. So are there any questions in the audience? And as time is progressed, I would be happy also to promote people to the panel and we can directly discuss. But I think there's here one thing is question. Do you think it is possible to mimic the definition of pivot polytope for more general convex body? For instance, for spectra, tetrahedron or a semi-algebraic convex body.
Thank you very much for this question, Chiara. It's a great question. Thank you very much because it allows me to say a little bit about the construction of the polytopes, and I should have said that. So in the fiber polytope construction, I know you have wonderful papers by Chiara and collaborators on generalizing essentially fiber polytopes because you take the sum of the fibers for convex bodies, right? So it has a natural generalization to convex bodies. I think this is much more tricky because I tell you how we construct these polytopes. These are essentially Minkowski sums, but not of slices, but you need to look at just local slices, just what happens at a vertex on the improving edges. So you need to look at the improving edges, and that gives you some kind of simplex. So it's a Minkowski sum of simplices in some sense. But so that's very combinatorial. You really need to know the vertices, right? You really know, we are in our construction. I mean, maybe Raman have a different idea, but I think in our construction, we depend greatly on the graph of the polytope. I don't know how to overcome that for general convex bodies, you know. Yeah. Thank you for your question.